Welcome everyone to A&L Canada Laboratories webinar on interpretation of tissue analysis and foliar feeding. Talk about plant analysis. A&L Canada supports analysis with a huge library of analysis and results of crops all the way from alfalfa to zucchini and all stages of growth. Our interpretation is based on the majority of what we've done in field, plus some other research from around the world where we've developed some of these ranges. We look at crop nutrition. Crop nutrition starts with a good understanding of soil fertility and fertility variability within the field. The main thing we want to look for before we design a fertility program is looking for hidden hungers and address the hidden hungers with supplemental feeding, either top dress or foliar nutrition. Plant analysis and foliar feeding supplements this well-balanced soil program, and we use tissue analysis to monitor that throughout the season. So why do we use plant analysis? Well, we use it to identify which nutrients are deficient at specific stages of growth, and this is key and important to understand that stages of growth change and ranges change throughout the season. It allows us to do a more cost-effective determination of how we're going to treat the deficiency or how we're going to deal with the issues that exist in the field. Analysis tells us the extent of the deficiencies that may occur, or also tells us at what level the nutrient might be in concentration that might tie up something else, so we can address that as well. And again, it basically removes all the guesswork. So why do we use plant analysis? Well, we use it for troubleshooting, that's one, so we want to identify what's happening up there, but more importantly, you should have a tissue program designed to deal with problems before they occur. We'll talk about that throughout the presentation today and how to use the tissue sample program to respond to nutrient deficiencies before they become crop yield loss, a reduction or quality issues. So we're going to use it for more of a crop monitoring tool than we are for troubleshooting. So what does the analysis actually tell me? One, we can diagnose issues, and again, looking at bad areas versus good areas to understand what is actually going on so we can put things in place to correct it for future crops. In this approach, we're using paired samples. But whenever you're using any kind of a tissue program and you see these visual deficiencies or problems, always take a picture. This library of pictures can help you in the future identify things very quickly. So look at nutrient concentrations and just at what stage do they become a problem, either too low or too high. First of all, visual deficiencies are quite easy to diagnose. Most things are very typical of that particular nutrient deficiency. The low levels, however, are the ones that we really want to address because they're what we call hidden hungers. And they may not be visual, but they're causing you either yield or quality issues that you can't see. So here again, the tissue analysis helps us deal with that. When we get in the sufficient range, sufficient to high range, that's where we want to run most of our nutrient levels in the cropping system. And basically what we want to do is we want to stay in this range, and if it drops to the low range, we want to start topping up that nutrient before it becomes deficient and a point of no return. Excessive levels are also a problem because they tap other nutrients, and that's why we don't want to use a shotgun approach to treating nutrient disorders. We want to treat individual disorders as they occur. And then excessive levels also cause us real problems, and it can actually be toxic. So look at hidden hungers and recognizing deficiencies. First of all, the easiest one is a visual deficiency symptom, which are easy to identify in crops and oftentimes don't need a tissue analysis to identify that. Then we have our hidden hungers that we cannot see, but they're causing us yield and quality issues, and we need to be on top of that, again, with some kind of a tissue monitoring program. The other one that doesn't get addressed often enough are the super optimal nutrient requirements by crops, and these are crops that are put in early, they're put in ideal conditions, and the crop is set up for a fantastic yield, but the soil around it can't support that yield, and we get a huge crop growing that needs supplemental nutrition, and oftentimes we walk away from these crops just a little bit, I guess, confident the crop's going to be there, and then the next thing we know they crash and we lose the crop. So when you have an absolutely fantastic crop coming, it's more important to monitor that crop than it is some of these other crops to make sure we don't run out of gas before the crop's actually harvested. So we want to monitor the crop in progress. Early tissue sampling to determine critical nutrient levels is key. Anything we can do prior to that crop going from vegetative to reproductive usually will solve a problem. The longer we leave it, the harder it is to correct that problem and the more yield and quality we lose. So early detection allows us to put correctives in place quicker. We use this monitoring program we're going to talk a lot about today to monitor particularly nitrogen levels throughout the season. This particular nutrient we can apply to a crop very easily, and we do oftentimes over-apply nitrogen and cause ourselves more issues with quality problems in crops. So it's a lot easier to spoon feed nitrogen and monitor it throughout the season. But as with all the other nutrients, we need to monitor those levels throughout the season as well. The importance of nutrition through the season and identifying where these are at different stages is key. So we need to know what stage of growth you're at on your tissue report so we can give you the ideal ranges. And you need to know what stage of growth some of these things will change. When we go from vegetative reproductive, nutrients can run short very quickly. So having what we call our plant monitoring program in place so that you can keep an eye on where those nutrients are going prior to them becoming a problem is critical, particularly at these different physiological stages. When we have a nutritional stress of any kind, disease pressures will become more of a problem. And again, this analysis removes a lot of the guesswork. So at A&L, we have a program that is no more money for you to do. It's just additional sampling. It's called our Plant Monitoring Program, or our PMP program. You can sign up for that ahead of time if you know what fields you're going to work with, or you can simply address that as you send the first sample into the laboratory. How this works is it's a sample setup that looks like this, and each element having its own chart on the bottom of the page with the different sampling dates listed as such. And all that does is gives you a little better visual interpretation of the trend line of that nutrient as it's growing through the season. And growers can use this to just get a better understanding of what direction the nutrient's going to anticipate where it might be come the next sampling period. So we look at tissue programs. Oftentimes they're used the wrong way. They're used for a diagnosis, and they're not actually, a sample's not taken until we see a problem. And usually when that happens, it's almost too late to do anything. With a plant monitoring program, you've done a good soil testing program on your farm. You know where these deficiencies might occur. So you put a plant monitoring program in place to monitor how well you've done in delivering a good fertility program. And as you see these trend lines going south on you, you can actually start doing supplemental feeding before they get to what I call the critical low. So we use crop monitoring programs for all kinds of reasons, such as in apples with potassium and a number of different things that potassium deficiency causes in something like an apple, or phosphorus and some of the issues that are centered around phosphates. We use it for monitoring nitrogen levels in different crops like potatoes, with nitrate and nitrogen. We use it for calcium monitoring in crops, for shelf life and storability of different crops that we grow. So it gives you kind of an idea that what's going on in that crop as you're going through the season so you can respond to it. Here's a situation where a grower had a plant monitoring program in place on tomatoes. This particular disorder on tomato is a calcium boron problem that usually comes in when you have a little bit of a spell of cold weather. These tomatoes are not marketable anymore, and this grower came to me and said, what happened to this crop? It was a beautiful crop, and I basically lost my last couple of set. Well, we look at his tissue sampling history and just the different samples he took, and right from the start he had a calcium deficiency and a boron deficiency. Well, if you're going to do the monitoring program and have this information, you should be doing something to correct it. This particular grower did nothing to correct it and just watched it go through the season. And the reason for that was, initially back in this stage, the fruit did not exhibit the deficiency or disorder, so they thought they were fine and kind of rested on their laurels. And then when the right conditions occurred, they had this issue. So again, pay attention to the data. The data does support what we know will cause problems. If you don't respond to it, do not let these nutrients drop into what we call the point of no return. So the forms and paperwork to fill out to become part of this program, the enrollment form, which can be done ahead of time if you know how you're going to set your field up, or again the submittal form, which you would send in at time of submitting the sample. Either way can enroll you into the program. So we're collecting tissues for laboratory analysis. Things to avoid: disease areas, insect damage, mechanical injury, spray damage, or stunted growth. They're going to have an impact on what the results look like. Now, if you're looking for what disease it is or what kind of spray damage it is, obviously that's where you want to sample. But if you're just looking for overall nutritional values, you want to avoid these areas. Things to consider when sampling, obviously the part of the plant that you're going to sample, because that's based on how we make our guidelines. The age of the plant, so the physiological age helps us understand and give you the right information back. The number of plants, or number of plant material, amount of plant material that we want you to submit for analysis, and then the sampling area. This is important because we need a certain amount of material to the sample, but we don't want you to go too wide in an area where you might get outside of a sampling area that might start mixing up the results. So in plant analysis, we want to use a proactive program beginning very early in the season. Sample the most recently matured leaf of a plant if you don't have the information on what part of the plant to actually sample. And again, as I previously said, don't mix up management zones. If you've done a soil audit or a site-specific sample of the field, you want to pick your management zones so you don't mix up different nutrient levels in the tissues that you analyze. We need about half a pint of loosely packed leaf material for doing the analysis, so it gives you an idea on how much you need to supply. Do not pack in plastic and ship overnight. And again, and this seems a little bit redundant and overkill, but oftentimes we get samples in here and somebody does not tell us what stage of growth it's at. Online, we have a plant sampling guide, and here you can see listed all the different crops, the stage of growth, what part of the plant to actually select to send in for sampling, and this can be accessed on our website. Or simply, as I said before, you're always looking for the most recently matured leaf when you send it to us. Remember to do the paperwork. It's important. Our technicians don't bring every sample to the agronomist to look at this plant before they send it in. So we need you to do that bit. Tell us what the crop is, what the stage of growth is. And if you have any comments on what you suspect might be a problem or things you're looking for, you need to put it down here in special instructions. So we talk about different crops that we analyze. Again, we have a whole range of ranges. Some of the ranges might be the same in certain stages of growth, but we will specify the part of the plant we want you to test at certain stages in some cases, so we need to have that information. When you look at small grains in some plants, we might start out with the whole plant, but shortly after that we'll tell you to select at certain stages certain parts of the plant. The reason for this is the database we have is based again on the most recently matured leaf, and if you mix up very young tissue with old tissue, you're going to get information that's really not going to help you out. Again, in the case of a lot of grains, we have stages of nutrient status that go right from very, very early growth right through to harvested grain. So again, we need to know the stage. Likewise, on any crop that you might be growing, we'll ask you at early stages of growth, you'll probably pick the whole plant, but later on we'll take selected areas of the plant that we'll ask you to harvest. So you need to have a proactive nutrient program. Locate and identify potential deficiencies, or what we call hidden hungers, based on either field information or soil analysis. Based on that, you'll have additional supplemental applications and nutrients. And again, timing is critical. In our programs, when using a plant monitoring program based on a nutrient disorder, we might recommend an application of a nutrient by foliar or a top dress long before you see a deficiency or long before it shows up in a tissue sample, anticipating that problem to occur based on previous information. Use tissue analysis to monitor or fine-tune in-season nutrient requirements. What we're talking about here is, even if you have the best fertility program in place, your soil levels are basically in good shape. Again, you might have a super crop growing where it's going to have big demands on that field. Or in every year we have certain environmental conditions that create a deficiency right across the country. That might be boron one year, might be magnesium another year, and it's just an environmental factor that creates these deficiencies, and they'll be there. The case of something like manganese, it's only usually found in parts of the field. You need to know where they are and sample those areas and identify those. In the case of this particular nutrient in a fertility program, we may recommend that you put a granular program in place to fix those levels. But in the case when you're very low, you're not going to see that fix from a granular application in the first year. So you're going to want to look at a tissue program in place to supplement the granular program until this condition is actually corrected in the field. And that, again, that will start before you see a visual deficiency or before a tissue sample actually shows that up. So we're doing it in anticipation of a problem occurring. So tissue analysis, when you look at how to read this thing, it's not like a soil test. It's sometimes very counterintuitive to what we would believe is going on. Your best tissue sample will come off your worst field. In other words, you could have a tissue sample that looks absolutely fantastic, but that usually means you don't have a crop. If you're growing a crop that is really performing for you, your tissue sample should drive you crazy just trying to keep up with those nutrients. So think of each and every one of these little bars as being the fuel gauge for the tank of that nutrient. So this is going to basically monitor each and every nutrient. Early in the season, we want to start out with levels, all up in the high sufficient zone. So all these bars or all these tanks should be full starting out in the early season. As that season progresses, these levels will drop off as that crop is using the fuel. The smaller the tank, the faster these obviously drop off. So again, just because you're losing nutrient levels or these bars are dropping does not necessarily mean that you have a poor crop. Matter of fact, it probably means you have a really good crop unless all these things have tanked. We want to catch this, if it be potassium or zinc or manganese, we want to catch it before it gets into the deficient zone. So as we see this thing heading south on us, we want to start top dress applying or foliar feeding that nutrient to make up that or fill up that tank to go the distance. So again, think of these little bars as fuel gauges for that nutrient. We want to be topping up that tank before it becomes a problem. If I'm only a mile from home and I'm almost empty, I'm okay. But if I'm halfway through the season and I'm approaching empty, we better start topping up that tank. When we look at nutrient information within the crop and understanding tissue analysis, we also have to understand the relationship of these nutrients and some of the interactions between one another. So I'm going to spend a few minutes here going over some of the simple interactions you may see, but talking about how these things actually occur. In tissue analysis, something like nitrogen and sulfur relationships are real, and be able to looking at this nitrogen-sulfur ratio in your tissue can also help you avoid deficiencies in that crop. One of the biggest issues we have in all crop production is this nitrogen to potassium relationship. Most people don't realize that a crop uses a pound of potash for every pound of nitrogen it actually uses. We can supply 75% of the nitrogen to a crop in a cropping year, but only about 15% of what we apply to that crop that year gets into the crop. So we're relying on a lot of soil reserves to supply the difference in potassium. So look at this balance between nitrogen and potassium and look at how this crop responds. Early season, for every pound of nitrogen a crop uses, it needs 3 pounds of potassium. As we progress through the season, get into the later part of the season, it's 1-to-1. But in the early season, this crop has a big demand for potassium. So what that is telling us is that potassium plays a major role in how this basically foundation of this crop is set up, and basically how the yield and performance of that crop is going to be set up for the rest of the growing season. So your potassium levels in your tissue sample early season are very, very important. If you start out in the season, your potassium levels are low, and it could be because we've got cold, wet season, which always has a problem with potassium. You need to start putting supplemental potassium on over and above what you've already placed in that field, because we need to get that back up into range. If you don't do that and you move into the next physiological stage of that crop, you'll never catch up. So we need to really look at this and pay attention to this early in the season, because not only yield, but more disease pressure and quality pressure comes with that low potassium early, particularly things like fusarium. And for the most part, we're just not using the right amount of nitrogen and potassium for this balance in most of crop production in North America. So you look at that relationship. This is an early season GS3 stage for winter wheat. And you can see here this particular sample has low nitrogen, potassium, and boron. And this isn't by happen chance. The synergies between nitrogen and potassium and boron are very real, and they're real for a reason. We look at the nitrogen-potash relationship. For every pound of nitrogen this plant takes up as nitrate nitrogen, needs a pound of potassium. So for long distance transport up that xylem, up into that plant, we need 1 potash for every nitrogen. Once up inside the plant, nitrates break off to form the amino acids, the proteins, the carbohydrates. Potassium picks up the sucrose from the leaf, loads it into the phloem for distribution throughout the plant to the root system, to the rhizosphere, to the developing crop that we've got out there to convert back into carbohydrates. So if potassium is low in supply, nitrates actually accumulate in the plant because there's no place for it to go because we haven't got the warehouse emptied. So an accumulation of nitrates in a plant tissue does not necessarily mean we've overapplied nitrogen. It could be for 2 reasons. One, not enough potassium to take the sucrose away, or maybe boron levels aren't high enough to maintain the phloem to build this conduit to move the sucrose back to other parts of the plant for redistribution. So there's some things happening here between those 3 nutrients, and you need to understand that when you look at a tissue sample because sometimes it can be misunderstood. This is a tissue sample on early potatoes from a consultant that I worked with, a new field. She called me up and said, we got a problem. I haven't changed my program at all, but I've got excessive nitrate nitrogen in my petals. And she knew this is a problem with tuber development once I get beyond my optimum stage. And she said, I don't know what I did. It hasn't rained, so I don't know why nitrogen are releasing the way they are. I haven't put more nitrogen on. I just must overuse nitrogen. Well, that's not the case, but that is a knee-jerk reaction. In the case of potatoes, if we have a cutback in nitrogen, we can increase verticillium or just crop performance in general. If you look at her tissue performance right from the start of this crop, she was low in potassium and boron both. So this is not a nitrogen problem or overuse of nitrogen. This is a nitrogen use efficiency problem because of low potassium and boron. So when you look at a tissue samples, you need to take these different parameters you need to look at these 3 because they do play a role together, do work together. So look at the phloem of the plant, again maintained by boron. This is a phloem. This is where all the nutrients are loaded into, the sucrose is loaded in for redistribution. Things like boron and magnesium come up by respiration by xylem with water. So there's these 2 conduits we have to look at and just how we maintain those in the plant. This phloem and how this phloem is maintained throughout the growing season is very important. So we're going to talk a lot about boron and boron nutrition and how it plays such a role in redistribution of the nutrients throughout that plant through the growing season. We look at boron as a plant nutrient for a number of things it does in the plant, but again, more and more working with boron as it applies to how it maintains that phloem. And because boron is taken up by the plant through respiration, even if your boron nutrition is good in your field and you've done a good job of applying boron, if you have a hot, dry spell, boron can become deficient just because of poor respiration and things start to fall apart. In boron deficient tissues, cells cease to divide, but elongation still continues in these growing zones. And what happens is that phloem basically breaks down and becomes a bit of a problem. We know what boron levels have to be in fields, but even if we have these levels in dry conditions, we still might have a boron problem. So this is what a phloem looks like. You can see nice structure of phloem cells, nice conduit for movement of nutrients throughout that plant. And this is where we have boron deficiency. So the phloem is very much disrupted and just inhibits the flow of those nutrients, that sucrose, throughout the plant for redistribution. This can be very subtle. A lot of levels we have in literature out there are probably too low for what really is going on in the plant. This is a potato plant in a season where the crop looked very good, but this is a very subtle boron deficiency in potato. And in this particular case, this is robbing us from yields. Now, the ideal boron levels for potatoes at this stage of growth is greater than 33 parts per million. And we took this plant back in the lab and analyzed it. This leaf actually come back in at 27 parts per million. So it doesn't take much of a change from what I call adequate to being deficient to cause some real problems. We get funny shaped leaves here, but that's not the problem. We've got a phloem inside this plant that's starting to get disjointed and moving of that sucrose from the leaf down to the tuber is challenged. We use a lot of boron application late season for pushing some of these sugars and realigning that phloem late season, just so we get better movement of sugars to the tuber, and we see decent yield responses from that. Not that we want to use this as a rescue treatment late in the season with rank green crops, but we want to make sure we maintain that phloem, and for the reason for it, that any time that phloem is disrupted, we're losing yield. Also plays a role in this particular crop with quality. This is phloem disruption early, so we get poor redistribution of sugars. We have accumulation of reducing sugars in this part of the potato. In this case, the stress happened mid-season. In this case, it happened late season. And what that looks like in a finished product is either sugar ends or dark ends in the potato that is an issue for the processor, and the farmer is deducted for that. Boron deficiency, we see it on all crops, oftentimes just gets let go. This is boron deficiency in canola, and we see it fairly extensive in Western Canada. Causes mid-stem blank seed and just all kinds of issues in production. So you see this type of thing, just poor seed production. So other things we talk about in interactions is we may have adequate levels and still see deficiencies. This is a cucumber in a glass house where we have good levels of calcium and good levels of boron, and our calcium to boron ratio is 400 to 1, and that's where you want to be with most crops, is 400 to 1. That tissue sample, we've got lots of boron, as you can see here. We've got decent calcium, and our boron to calcium is 400 to 1. Here we have a situation where we have some problems. Again, we've got excellent boron levels, but our calcium is way too high, and our calcium to boron is 586 to 1, and we have typical dieback of the growing point and boron deficiency showing up. So sometimes just an over-application or too much of one thing, even if you have adequate levels of another nutrient, can cause you a problem like we see here in the cucumber. So we look at nutrients and nutrient applications. We don't want to take a shotgun approach. We want to use tissue analysis to understand what we have to apply to keep this crop in check, because there is relationships between these nutrients, and over applying one will antagonize another, or again, as I showed you with the case of nitrogen, potassium, and boron, they work in synergy, and we need to make sure we understand that when we look at overall nutrient reactions. So we look at how this plant responds and how it produces the energy to grow. This plant in early stage of growth will take up a salt. That salt of choice is potassium. It takes potassium inside the plant through an active process that takes energy. And it gets that energy from the uptake of inorganic phosphorus that it converts from inorganic phosphorus to a form of phosphorus that it needs to continue life, provide the energy for growth, and produce the simple sugars that produce the carbohydrates to make the crop. You can see here, in order to do that, we had this enzyme that's synthesized with potassium to help this process. And then we had magnesium that was actually robbed from the mitochondria in this case, that actually bridges this gap to produce the ATP. In a plant, the plant stores energy as ATP. This is actually magnesium ATP that it stores as energy and uses when the sunshine goes away and we respire overnight to provide the energy to keep the plant growing throughout the rest of the growing season, or that day. Magnesium also exists as part of the chlorophyll molecule. So we've got magnesium being used in a process of phosphorylation, which we just talked about, the conversion of phosphate to ATP. And we also have it as the center of the chlorophyll molecule. Now, when we do a tissue analysis, we see it as chlorophyll, not as it's being used in phosphorylation. And this causes a bit of a problem in understanding tissue samples, because when that plant suspects or feels like it's running out of magnesium, it starts storing magnesium for chlorophyll as opposed to using it in the process of phosphorylation. So we lose yield and potential because this crop has gone into kind of a salvation mode where it's just storing magnesium to keep it from running short of chlorophyll. So when we see this, we actually see high levels of magnesium in a plant that could actually be short in magnesium. And let me just explain that with this tissue test. This is, again, another potato field. This field has over 200 ppm of phosphorus braid P1 in the field. This grower is using 150 pounds of phosphate down the tube for phosphorus in planting this crop. Yet you can see here in early season, again, this phosphorus level should be up here at 0.5 to 0.6, and we see it at 0.27, not even within the ranges. So we got a bit of a phosphorus problem, but we've got magnesium levels here at 0.33 within the adequate range, but magnesium is not being used in phosphorylation. This plant is actually starting to store magnesium because it picks up the fact that it's short magnesium in the soil. Soil test levels are quite low in this particular case, less than 50 parts per million, about 3% saturation on the exchange complex. This grower is using lots of potassium in this fertility program and in further inducing magnesium deficiency. So when we look at a tissue test, keep in mind that this relationship between phosphorus and boron and magnesium are real. Going back to that whole scheme I showed you on phosphorylation and how magnesium actually helps the plant convert phosphorus into ATP. We look at magnesium deficiency occurring in a plant. Here we have a melon leaf. You see this yellowing here of the leaf tissue. This is the plant actually robbing magnesium from the chlorophyll to help it at this delicate stage going into flowering. Anytime a plant goes from vegetative to reproductive, you can find these little yellow spots on the leaf as the plant is trying to rob or use magnesium in that stage of growth when it's using lots of energy. If our magnesium levels are in the field are adequate, these spots go away as the plant replenishes the magnesium supply that it's used at that stage. If magnesium is short in supply, these spots don't go away. They become necrotic, open sores, and open areas of infection, particularly for blight. So look at tissue analysis and monitoring tissue levels. Phosphorus levels, we want to start out like this, and they will gradually drop off through the growing season as this plant produces the carbohydrates and goes through to maturity. Magnesium starts out someplace just below that, and as this plant grows, magnesium will drop just a little bit as it goes into reproductive stage, and then it gradually increases as the phosphates drop off as we go to maturity. If we have a situation where our magnesium levels are low, this plant's going to start storing magnesium, and we get this inversion of phosphorus to magnesium early in the season, and basically this crop's going to defoliate, and we're going to lose this crop very early. So looking at tissue samples such as this one, one thing we see here is we started out the door too low in potassium, so we've got some yield performance problems starting off right at the get-go. And we've got, you can see here, this inversion between phosphorus and magnesium. This is not good. This is going to tell us that, and again, this is a potato crop, that we're going to run into trouble very quickly. And you can see here, very shortly after we get going here, magnesium starts to ramp up, and we've got a problem occurring here with the plant accumulating magnesium. So that's not a good thing. Here we got another case where phosphorus levels start out where they should, magnesium starts out where it should. This is very good. This is where we want to be, where we want to see this crop go. However, we have a bit of a problem here at this stage. We have a dry spell happen. Boron drops right off. The other thing happens in dry spells is magnesium is also moved to the plant through mass flow, so we have a bit of a magnesium issue. The plant starts to store magnesium. It ramps up very quickly to 0.86. This is kind of the trigger point in potato petioles. Once you get close to 0.8, you want to start applying magnesium because the plant is actually storing magnesium. So what we've done here, this grower's done, is actually come in and applied some boron and some magnesium. We can see that the magnesium levels actually dropped, and we maintained this crop and took this crop to a decent yield. So the trigger points occur on all crops for something like magnesium and boron. Again, in the case of potato, we want to stay above 0.33. For boron, we want to stay below 0.8 but above 0.3 in magnesium. And all these ranges mean something to us when we start looking at tissue analysis. Here again too, we start at phosphorus at 0.56 with magnesium 0.43. This is where we would like to see it happen, but this is a little bit later in this particular season. Again, we had a problem with drought. Boron started out low to start with, and then we had a critical incident here And again, you can see as soon as that happened, we started to see magnesium ramp up. We quickly got into trouble. Coming in here with an application of both boron and magnesium, we saved that crop. But again, we were running into trouble before we responded. So in the case of something like magnesium, it's not that easy to interpret on a tissue samples. You can actually be magnesium deficient for anywhere from 20 to 30 days before it shows up on a tissue report. And again, that's because we're reading it as chlorophyll, not as it's used in phosphorylation. And what's happening here is accumulation of magnesium. There's poor movement of sugars to the plant, and things are just starting to go backwards. Above ground parts of the plant, you really can't see it, but very shortly after we have magnesium deficiency, you can see what happens to the root growth. We have a real problem happening at the root level, even though you don't see it quite as visible in the above ground parts. And this is low magnesium versus adequate magnesium root growth in wheat. When we look at the accumulation of magnesium, and I showed you how we had those little yellow sores that could turn into necrotic spots and open points of infection. Manganese plays a major role in the plant's ability to fight disease. Magnesium and manganese compete. So when we have that accumulation of magnesium, what is happening is the plant is actually it's competing with manganese, and we have poor manganese supply to help this plant prevent disease. So whenever you have a high magnesium issue, we might suggest you start spraying magnesium. You should also look at putting some manganese with it to help support the shikimate pathway so we don't have more disease pressure. We use magnesium in other crops early in season to push growth. Again, cool, wet growing conditions, we're a little bit behind. Putting magnesium foliars on will actually push energy into the plant. Again, that conversion to ATP and push energy. In the case of potatoes, when we have poor row closure, regardless of what the magnesium levels are, we'll put some nitrogen and magnesium on to push energy into this plant. When we look at understanding total nutrition, we look at how soils respond. This is an example of high magnesium soils where we get in a situation where magnesium is actually not being supplied because of high mag soils. This case here, we have magnesium levels in soil actually in a good range, but this is a crop that has a real demand for magnesium, and we're not applying all that much. We're applying a lot of potassium. And when we look at what's going on here, we have 15.3% magnesium here. We're only putting 30 pounds on, and we can see here we're a little bit on the light side for magnesium in this crop. So we're struggling, although here our phosphorus is working, so the system's working for us. We're not critically deficient, but we need to keep an eye on this because we could drop in the critical deficient zone very, very easily. So when I look at this, I'm not really concerned. My phosphorus is working the way it should. I don't have an inversion between phosphorus and magnesium, but I'm on a verge of that being able to happen, and this crop get into trouble real quickly. This particular case, we've got percent saturation of magnesium in the field at 24.3%. In soils and soil chemistry, when you go over 20% saturation of magnesium in soils, they become very tight and anaerobic, and things don't move well, and the plant actually starts becoming short in magnesium. It actually can't take up magnesium, although there's all kinds in that field. So a high mag soil can actually be magnesium deficient. And that's what we're seeing here in this early tissue sample. The phosphorus level starts here. We're starting at 0.79, which is almost close to that 0.8 I talked about, even though when you look at the magnesium that's in this field, because it's a tight anaerobic soil condition with over 20% saturation of magnesium, we're seeing magnesium deficiency show up on that tissue test. Difficulty here is to explain, we've got all kinds in the soil, and for somebody who doesn't understand this relationship, we got all kinds in the tissue. So what's going on here? What's wrong? Somebody who doesn't understand this relationship say there's nothing wrong with this particular picture. I'm telling you, this is a problem. So here again, we've got a severe issue with phosphorus starting out early season low, 0.93% magnesium already. This is a magnesium deficiency, not a phosphorus deficiency. We need to respond to that. This is a good test. We're looking at where phosphorus should be early, where magnesium should be. So things are good in this case. that's what we want to see. We see this on all crops. This happens to be barley in Western Canada. Severe magnesium deficiencies, just no magnesium availability. We're starting right out the door very, very low in magnesium and some severe magnesium issues in this particular cereal. And we see this a lot of times, and sometimes it gets misdiagnosed for disease. Here again, high mag soil, over 20% saturation in that soil. This is what the crop looks like. You see this beating of the chlorophyll. This is magnesium deficiency in cereals, and that's what it looks at as it gets very severe. A lot of people mistake magnesium deficiency for barley yellow dwarf virus. This is actually magnesium deficiency. This is what BYDV looks like alongside magnesium deficiency, so they can be easily mistaken. We also talk about magnesium. We have to also keep in mind what it does for that leaf surface, and because of its relationship with chlorophyll, we think of magnesium as kind of the suntan lotion for plants. Magnesium levels at adequate levels actually help the plant with photooxidative damage. In other words, help prevent it from extreme sunlight and sun conditions. Now, looking at other relationships and interactions between nutrients, as we've gone through that whole process of converting phosphorus to ATP, we store that energy. We get lots of energy left over as the sun comes out the next day. So we're going to convert some of this excess energy into carbohydrates. So it'll take and convert that to this simple sugar, and that simple sugar goes through this process. And with adequate levels of boron, it will go through this process and make up the hemicellulose, the pectins, all the good things that make the crop that we grow. But this can't happen at marginal levels. Even at marginal levels, what happens to that sugar is it goes through this fermentation process, and these quinone phenols that are developed, these phenols actually attract insects and disease. So again, how that plant responds and that relationship between phosphorus and boron becomes critical in the path of conversion of that simple sugar to a complex chain of carbohydrates that makes up the plant that we work with. So I said that it attracts insects and disease. I showed you that melon plant earlier with the feeding on the flower. When we see any insect that's actually chewing on leaf or flower material, we know it's a phosphorus-related deficiency. And that phosphorus deficiency could come from low nitrogen availability that reduces phosphate uptake. It could be because of low magnesium, as we talked about, or boron, or phosphorus itself, where we get this accumulation of phenols. If we have issues with leaf-sucking insects, aphids, mites, hoppers, it's a potassium deficiency, and these particular insects are looking for a particular non-essential amino acid called asparagine, which is necessary in the dietary process for reproduction. So they become an indicator that something's not right. This is diamondback moth in canola. You see a lot of feeding here. This is Dr. Lloyd Dosdale's work out of Saskatchewan, and he basically looked at the response to leaf feeding based on increased phosphate application to this particular crop. And you can see here the amount of damage as he increased his phosphorus application to that crop. And another thing we find in canola is that this particular beast here, we can basically control with adequate boron nutrition. So again, that feeding and insect control because of with phosphorus. Here we have low potassium plants a few years back in Michigan. We had a real problem with soybean leaf aphid. The entomologist did some work on just what that occurrence was all about, and they showed soybean aphids reproduced faster and larger numbers with K-deficient plants. And the reason for that, again, is already mentioned, that they're looking for this non-essential amino acid, asparagine. It's a necessary dietary source of protein for these insects to reproduce. So we look at potassium deficiencies. We've talked about the nitrogen-potassium relationship. It's real. We see potassium levels here in parts per million in the top 6 inches of soil that would look to be adequate, but on a percentage basis with the high mag in the soil and the K to magnesium ratio here, this field is actually very low in potassium. And looking at early barley pre-boot stage, we're seeing that this plant is coming in much lower than we would want for potassium at that stage of growth. Likewise, early season wheat from Western Canada, again, we're seeing deficiencies. So we see this quite often. It gets misunderstood or let go because we just don't do a proper job diagnosing it. Here again, more potassium issues. This happens to be canola. Although we're within the range, just slightly above the critical range here. For this stage of growth, this is too borderline and too critical, and you will see deficiencies like this showing up in canola, even though you're just kind of borderline on that potash range. I want to talk a little bit about foliar feeding and foliar nutrition. We need to understand the differences between nutrients that we're applying. We talk about foliar feeding versus leaf feeding. We look at leaf feeding. This is an application of high analysis material at low levels that stimulate vegetative growth, but don't necessarily enhance nutrient levels significantly. So we use this if we want to get a crop through droughty conditions, keep sugars moving within the plant. We're putting a fungicide or insecticide on, putting a little triple 20 with that, helps the plant overcome some of the shock from that, droughty conditions, that sort of thing. That's a leaf feeding program. Not trying to change nutrient status, just keep sugars moving within the plant so that the root system doesn't go dormant on us. Foliar feeding is the application of high analysis materials at high concentrations that will correct a nutrient deficiency or maintain levels that are required. What I mean here by maintaining levels is we might not expect potassium levels or phosphorus levels to increase significantly with a foliar application because it's a big push. But if we can maintain the level as this crop goes from one stage to another without seeing it drop significantly, we've accomplished something. So leaf feeding, what we're trying to do here is these young plants, as they're growing, are contributing to that leaf or that plant significantly. And as long as they're young and growing and still in that young stage, they're contributing photosynthase to that plant. At some point in time, they will become mature leaf, and they really don't contribute a whole lot. They kind of maintain their own, and actually closer to an older leaf, it can actually become a little bit parasitic to a plant. What we want to do is we want to extend the life of that young plant so it artificially feeds that plant longer or contributes. Or more importantly, we want to make sure that we keep this plant, this leaf, doing this sort of thing and not come up short too early in the case of a drought condition. So if you understand this relationship and these different nutrients, leaf feeding is something like a triple 20 or a soluble fertilizer we put on just to help the plant through stressful conditions. It's not really trying to change nutrient levels significantly. We talk about foliar feeding and trying to put something on a plant to increase the nutrient level. We also have to understand there's only so much we can do. In the case of nitrogen we can spoon feed very easily through the leaf. Other nutrients, not quite so easily. But let's say we're looking at zinc, and we want to go from a 20 to 30 part per million. That's only a push of 10 part per million, and we could see that happen, and we could do that quite easily with the materials in the market today. If we want to go from a 9% potassium to 11% potassium, that's 20,000 ppm change in leaf status. That is almost impossible to see happen. But if we have the right material, and we use the right material, and we can maintain that plant at the 9% as opposed to see it drop any further as it moves into the next stage of growth, we have accomplished quite a bit. Okay, so phosphorus, going from 0.22 to 0.24 again is a push of 200 part per million. And there's a lot to expect from any foliar nutrition. But again, if we can maintain or stop this slide, stop this phosphorus from dropping any further than this, we have accomplished what we're trying to do. So look at foliar nutrition. It's a simple principle. There's no magic to foliars. It's all about concentration of a nutrient. So Fick's law says the rate of diffusion across the membrane is proportional to the concentration gradient across it. In accordance to Fick's law, the higher the concentration of the solute, which can be applied to the leaf surface without causing damage, and the longer time it remains in an active state on the leaf surface, as in solution or solid in a liquid form, the greater the likely rate and the amount of penetration. So what Fick's law says is that we want to put a product on in high enough concentration that actually stays on the leaf surface. It re-wets at very low humidity and does not burn the leaf. And if we can maintain that, we can get a higher proportion of that into the plant. So when it talks about these formulated foliar products, I mean, the information is on the label of how these things work, basically. So factors affecting foliar uptake: leaf age, the older the leaf, the lower the uptake; temperature, surrounding leaf moisture. So the drier it is, the thicker the cuticle, the higher it is for harder it is for that nutrient to penetrate through the cuticle. Higher the crop load, the faster the uptake. Choice of the nutrient we're looking at, the type of salt we're using, and that's referred to as a point of deliquescence, and I'll talk a little bit about that here in a second. Concentration of the product. A 20% concentration is going to be much more effective than a 9% product, provided it doesn't burn the leaf. pH of the solution, we want to be someplace in the 4.5 to 6 pH range for most nutrients, other than things like potassium and boron. And then the use of these adjuvants and formulation products that some of these companies are using. Some companies will put a product in their formulation that actually increases the point of deliquescence, or it's a wetting agent or a sticking agent that helps with the formulation of the product. So we talk about choice of salt and point of deliquescence. There's quite a difference between these materials. Now this is just looking at potassium. Potassium carbonate, as opposed to all the other potassiums we've put on foliar, is far more superior than all these other products. And the reason being is that this particular product, not only has low phytotoxicity, we can put it on large concentrations. It has a point of deliquescence of about 44%, so it only needs about 44% humidity to actually go back into solution. So it wets very easily. So you look at foliar penetration of these salts, the point of deliquescence is quite important. You can see here the difference between calcium chlorides and magnesium chlorides at 33%, so very easily do they go back in a solution, but they have a lot of phyto with them because of the chloride component. But they are very effective in foliar uptake. Here's your potassium carbonate at 44%. Then you look at calcium nitrate at 56%. Still very good, both magnesium nitrate and calcium nitrate, but a little more phyto. And then all the rest of the salts are well above 90% humidity before they re-wet. So you look at point of deliquescence and all the different materials that we actually supply and use in foliar application have a point of deliquescence rating. Understanding that number helps you understand how effective these particular materials. And then you also have to look at what is the phytotoxicity of these materials. So in conclusion, we want good nutrition is important for yield and quality. At A&L, we focus on mainly quality. We believe that if you grow for quality, yield comes with it. We're suggesting you monitor the crop at critical stages to manage the crop inputs and just make sure you're topping up the tank through the growing stages. And then using the right products at the right time maximizes the quality and production of that crop. So with that, I don't know if we had any questions come in. We can answer a few questions, but thank you for listening. I hope you got something out of that webinar and that presentation. And the main goal here was to tell you that tissue samples are not as easy to read as soil samples in a lot of cases, and you really have to look at the relationship and interaction between the nutrients and understand physiologically what's happening in the plant when you look at reading a tissue test. So thank you for your time and attention.